Hi, my name is Andrei Drozdyuk, and today I would like to cover neural ODEs. So the first thing I'm going to show is some cool results from my personal experiments. Then we'll talk about machine learning part, and then dynamical systems part. So for those people who are not familiar with machine learning, they may find the first part useful, and for those people who are not familiar with differential equations, they may find dynamical systems part useful. And finally, we'll cover the adjoint method, which is what goes under the hood of neural ODEs. So for some results, here is an example of learning Newton's law of cooling. So here we can see the samples are in red. So the red dots here represents the samples that we have available for the different temperatures in time. So as the time advances, something cools down and it goes from 100 degrees here to something like 25 degrees. And as we learn the law using neural ODEs, we can see that there are predictions. The green dots are pretty spot on here. So another example is a chemical reaction rate law. So here we have three different reactants, two reactants and one product, and we can see their the reaction rate here progressing through time. And again, the true predictions are the dotted lines here. So this dotted line represents the actual true progression of the reaction, and the dots is what our neural ODE predicted after we trained it on just 5 points. So machine learning part deals only with the motivation and machine learning relevant subject. So what is a neural ODE and how is it motivated? So let's forget everything about differential equations and just start with a simple ResNet. So what is a residual network? Well, it's a sum neural network where we have the input. This input is multiplied by some matrix, and we have an output f of z0. In addition to that, we also have another signal where the z is also bypasses this matrix, and it's added to the output. So z1 is the sum of the output of the layer and the skip connection z0. So this we call the residual, and this we call a skip connection. And so that's why this is called the residual neural network, because it sums both of these components. Now, if you look at this next part, you can see that Z1 goes through F2, and so we get this term here. And then Z1 also bypasses this, and we get Z1 component here. So if you look at this, you can realize that output of every layer is basically the something done to the input plus the original input. So we can think of this as some big network, some big function f that basically takes z right here and uses a parameter theta, right? So it takes an input of z, passes it through the network, outputs some output, and the whole thing is parameterized by some parameters theta. Now, what if we could take these intermediate layers and just extract them to the side and reuse the same layer instead? Well, this is what we're going to do here. So if you look on the right side here, we're just going to have one shared layer, and the way we're going to use it is to replicate the ResNet on the left, is we're going to say, well, anytime Z0 comes in here, the first input comes in, let me call this layer with that, but pass it a t, and t represents the layer number. So let's say f of z0, comma 0, well, that's going to be equivalent to this call right here, right? This is going to be f of z0, 0. So this is the same as calling that layer with the parameter 0. So let me, as you can see, I have written it out here. This is f of z0 at 0. Plus, we're going to add the z0 that comes from here, right? So this goes both here and like that, right? So it goes through the shared layer on the right, and we just have a skip connection that's coming straight here. So the output of this is going to be z1, which is just f of z0 plus z0. Similarly, to calculate z2, we're going to call this shared layer with f of z1, comma 1. And this is going to represent our second layer plus the z1 input. So you can see that this way we can always compute any output we computed on the left equivalently by just calling the shared network on the right with some input, comma, and the value of t that represents the layer we want to compute the output for. Similarly, the z3 is computed as f of z2, value of t is 2, and the input z2. And so the output is z3, and if we check, it is equivalent to this output. So all we are saying is that our shared network, f of x t, has an additional parameter now. It has a parameter t, versus before it was just parameter z. So this is the first insight of this neural ODE paper, is that we can represent the ResNet as this other thing called ODE net, where each layer, each intermediate layer, can be mimicked by calling this kind of shared layer, in which we just increment the value of t. So the way I kind of like to think about it in a hacky way is the left-hand side here. We can think of it as some function f that's parameterized by z, the input, theta, and it also acts on z as the input. Another way we can think of it is like some function f that is a function of three functions, f1, f2, f3, where these functions are the intermediate layers. Now, if we show an instantiation of this function, if we call this function with some particular input, it's going to be f of z0, and if we start with some initial parameters, those are going to be theta 0. Now, these parameters are the parameters here, right? They are the parameters at each layer of this neural network. Now, if we go on the right, we can formulate an equivalent thing here for this ODE net, where we say, in addition to z and in addition to theta, we are also going to take t. So our whole network, our whole function f, is also going to depend on t now. So in this case, we can also think of it as like, instead of having three functions, f1, f2, f3, as having just one function, f, that's parameterized by some parameter theta, but that function f is now dependent on t as well. So this big F now is dependent on the shared network, the input, the t, the final t at which we would like to compute the output. And what is this final t? What do we mean by this? Well, imagine t is 2, right? If we look at our diagram up here, this was t of 0, this was t of 1, and this was t of 2. So here we have 1, 2, 3 layers. So t represents the number of layers in this neural network. So this function f is parameterized by the number of layers we would like to have in this neural network. So an example of a concrete instantiation of this function is if we pass some particular f, shared f, if if we pass some input z0, we pass the number of layers, which is because it's 0 based t, this is going to be 3 layers, and this is going to be some initial parameters theta 0 for our shared neural network. So in this way, if we look at it, we can kind of look at this thing on the right, or dnet, as some function of t, right? So what do I mean by this? Well, we can view the output z as a function of t, right? If we look up here, z3 really is a function where the t is 2. So that z3 is a function of t when t is 2. z0 is simply z at 0. z1, the intermediate value, is z at 1. z2 is at z2. And z3 is, this is, let's say, our final output. This is what we want to get at the output of a neural network. However, notice that we don't really know these z's. They're hidden. They're hidden inside the neural network. So if we continue, we can write this f, which represents our whole neural network, as a continuous function of t, right? So let's say that our initial value of z is z0, and so we can write it as z of 0 right here. And we can say that f is no longer a function of z, but we only need the initial value of z, right? We can say that f now depends on some initial value of z, depends on the t, which is how many layers kind of we want in the neural network, some parameter theta, and this shared function and what it does. So we can reduce this kind of f from knowing about every value of t to just knowing about the initial value of t, z, sorry. So this is the point where we are crossing over from machine learning territory into this dynamical systems land. This is the differential equations and ordinary differential equations and dynamical systems, which we'll cover in the next section. But for now, just to give you a connection between the two, this system that we defined right here above, this function, well, this function can be solved by something called ordinary differential equation solvers. And what this solver takes is the initial condition, which in our case is z0, the function f that represents the derivative or dynamics of this system, the initial time point, and the final time point. So this time, this final t, we can think of it as a number of layers, and the parameter theta, these are the parameters of this dynamical system. So what this ordinary differential equation solver does is it computes for us the value at t1, at the final value t1. And this value is basically the output of our neural network. And we can compare this value versus the true value, and this creates our loss. So by using this black box method, we can basically compute the output of our neural network. Given the input z0, then we have some black box. We can compute the output, which is z of t1. And once we do that, we can now compute the loss. And so the question becomes, naturally, is, okay, if we have this loss, how do we go and backprop through this ODE solve black box function? And this is the second insight of this paper, is the ability to backprop through this operation, which we'll see later in the adjoint method. Okay, so now that we covered machine learning part, we'll go over to dynamical systems part. This is for people who are not familiar with what ODEs are or what differential equations are. So what is a dynamical system? Dynamical system is a thing that can be described by two things. It can be described by some state that changes with time. So we might have, let's say, some position of some particles moving through space, and z of 0 might be position 1, 0, and then as it keeps moving, then at time 1, it might be at position 2, 0. So state is just some vector that describes the state of the system. The second part of dynamical system definition is some rule. This is some rule for how the system changes. And this rule is expressed in this form as a differential equation. So when you say how fast is z changing with time, you're going to say it's some function of time, state, and some parameters. So parameters are just different constants that show up in this function f. This function f is just you can think of it as derivative of z with respect to t. So once you have these two things, once you have the state and the rule for how this state changes with time, you have a system of, usually a system, many of these equations, a system of ordinary differential equations. You have a description of dynamical system. So when we have such a dynamical system, the solution of it is said to be a function. So if you think about it, the dynamical system is described by a bunch of derivatives. Well, if we integrate it, in a sense, we get a function z. And this z is a solution to this dynamical system. So to solve an ODE is to find a function, the derivative of which will yield us that ODE. So for example, if we solve this system, and we get z, we can now find what is z at some particular point in time. For example, z at 5.5. So we no longer need the rule for how the system changes. We can just query the system directly at some point in time. And another note here is that we are given the initial value of the system at some initial time 0, and why we need this will be evident later. So let's talk about finding a solution to a dynamical system a bit more. So given some dynamical system, f, right, this is just some derivative that tells you, this is just some function that tells you what is the derivative at some time t, right? And it's parameterized by these p's. So if we're given some initial condition, we're given this f, which is the rule for how the state changes, and we must find the solution. So how do we find the solution? Well, usually one simple method of finding the solution is called the Euler method, Euler method. And so Euler method says to find what the value of z at the next time step is, well, just take the previous value and add h times the slope at that previous value, right? So here we can illustrate it at the bottom. Let's say we start at point z0, and if we start at this point, we want to find out what is the function at point z1, right, on this line. What's the function at time t1? Well, the way we can do it is we can take z0 and add some constant h. Let's use 1 times the derivative of 0 times 0 of z0. And what's the derivative here? Well, let's say the derivative is like this. And if we take a step in this direction, we'll end up at this point. Similarly, we can proceed in this way and arrive here and then arrive here. And so what we have arrived at right here is perhaps what we wanted to find out, z of tn. And we have solved this system for this time point, tn. Now, if this is our real solution on the left, and this is our approximate solution on the right, we can see that it diverges by quite a bit. And this is one of the downsides of this Euler method. And there are other methods that try to get better and better, closer and closer to the true solution. The point here is that what I wanted to show you is that we can solve this system simply by this numerical kind of method where we start at some point and we keep going along the derivative. So this way we can find z of t for any point t. So this is what it means to find a solution to a dynamical system at some point t of n. So let's look at an example problem. This is a pendulum. So a pendulum is something swinging from some point, and we can see that this pendulum might be swinging this way or that way. Just by looking at the picture, we can't know. So if we describe the system, just the angle from the vertical is not enough to give us an exact definition of the state of the system. So another thing we want is this angular velocity, which tells us which way the pendulum was moving when the picture was taken. So let's go through a definition in Python or pseudo-Python how this could be solved. So pendulum, first we'll write a function called pendulum that takes all of these variables, parameters y, t, b, c, and y here is going to be our state. This is the definition of our state, and it's going to be composed of angle theta and angular velocity. Then we're going to take the derivatives of this state with respect to time, and this is just going to be dy dt, so derivative of angle with respect to time, derivative of angular velocity with respect to time plus, and this is the other component. So then we're going to return this derivative, and for the sake of example, let's assume that we have these constants b and c equals to these values here. And these are the parameters that I was talking about earlier. So if our initial condition is y equals to 0 is some small deviation from pi, and 0 as angular velocity, so that the pendulum is nearly vertical, the way we are going to solve the system for 101 points on the time interval from 0 to 10. The way we do it is we import this function called ot_int, and we just plug in our rule for how the state changes. We plug in our initial state y0, and we say over what period of time we would like to solve it, and for which points, so these 100 points, which we like the solutions, and these are the arguments, which are the parameters. So now that we solved it, we get some object called solution, and so we're going to now plot these. We're going to plot the first and second component of the solution. So this is how the solution looks, and we can see that as the time progresses, the angle starts off almost vertical and then starts deviating in one direction and another, so the pendulum is swinging. And similarly for angular velocity, it starts almost non-moving and then it starts moving in one direction and the other. And so this is the solution that allows us to get a value of the state at any point t. Alright, so now we'll go on to the adjoint method, and this describes how we're going to backprop through that black box ODE solve method. So starting again on the example of ResNet and looking at ODNet, we can see that the input into the ResNet is basically like an initial condition into our dynamical system. And so if we can somehow say, okay, if the input is the initial condition, and then we do a bunch of stuff, and we know how what the rule is for the changes from layer to layer R, well, then we can somehow compute the output here using the ODE solve thing that we did before. So this is what we do. We say that we define the output here to be the solution to some differential equation, where this differential equation f of z of t, t and theta, is going to be defined by our neural network. So we can think of this as that shared f that we had on the right here. And so our neural network now represents the derivative, not the solution. And if we integrate that derivative, we can actually get what the solution would be. So let's look at how this is actually done. So here, what we see in the top, if we look at the top part, the the z of t0 is the input into our neural network. And we can think of trying to get some output from our neural network right here. And how do we do it? Well, in usual neural network, we just multiply this by some matrix and we get this. But in ODE, neural ODEs, we can think of it as the initial condition, and we can think of our f, which is our neural network, as defining the derivative by which this thing changes with time, dz dt. And if we do think of it this way, we can use ODE solve on our network to compute the final value z of tn. So the way we get from the left-hand side to the right-hand side is by calling the ODE solver. And the question now is, how do we backprop through this? So all of this is a black box method that's doing something. How do we get our gradients? Well, what we do is we define this thing called adjoint, and this adjoint is basically dl dz. So this is a derivative of loss with respect to the final output. And we can treat this adjoint as a function, right? This is a function that has a value at some time point, at some t. So in this case, it's evaluated at tn. And so what we would really like is to evaluate it at t0. So we would like to go from here to here. Well, if we look at this is simply similar to the way we found out the output this way. We can treat this as the initial condition. And if we know how this changes, if we know dA, how it changes with respect to time, then we can integrate it backwards and get our a of t0. And this is exactly what we're going to do here. So if we're looking at this, this is the adjoint method and how it's different from a regular method. And we're going to call it continuous time backpropagation. So in a regular approach, the way we backprop through the network is like this. And for adjoint, we're going to define adjoint like this, dl dz. The way we do forward prop is like we saw. This was the ODE solver method. So this part is the black box. This is our ODE solve. That will just get us the point at some final value t. And then the way we're going to backward prop through this is we're going to take we are going to want a of t at the previous time step, given a of t plus 1. So if we have that, we just need this, right? And this is going to be the adjoint differential equation. This is going to be our rule for how it changes. So we need to find out what that is, and we'll see how to do it next slide. The second part is we would like to know, well, it's fine to know this. It's fine to know how loss changes with respect to the inputs, but we would like to really know how loss changes with respect to parameters. So how do we compute that? So let's continue first to understand how if we let z, right, our state, follow this differential equation, dz dt, where theta are parameters, we want to prove that the adjoint dynamics, right, the way this changes is equal to this. So if we can find this out, then we can solve backwards in time for our adjoint. And so the adjoint state is basically gradient with respect to hidden state at some time t. So in a standard neural network, right, gradient at some hidden layer t depends on the gradient of the next layer. So we can say that dl dh is this chain rule right here. But if it's a continuous hidden state, what we're going to do is we're going to say z of t plus epsilon is just an integral from t to t plus epsilon. And the chain rule can also be applied in this way. And we can say that a of t is equal to a of t plus epsilon times this quantity right here. And the proof is as follows. So dA of t, dA dt is equal to the limit as this goes to 0, and then we can do some manipulations, and we arrive at this quantity. So what we wanted to show is that the derivative of the adjoint with respect to time was this. And since we know every quantity in this equation, we can compute our derivative of the adjoint. So now that we know what our dA dt is, we would like to know what is our d theta dt, right? Now that we know what our dA dt is, we would like to, when we integrate a adjoint back to the time of 0, we would also like to get the loss with respect to the theta, to the parameters theta. So how do we do this? Well, we can view theta as just another thing that changes with respect to time. It has its own dynamics, and because it doesn't change, we can say that d theta dt is equal to 0. And so what we do is we combine all of these things into a single state. So if you remember, before our state was just z, well, now we can add another component, theta and t, and we can package them all together and say that these things change in time as well. And so we call this augmented state. And now derivative with respect to this augmented state is going to be our f. And so this is equivalent to this. And so we can define our augmented adjoint as this three-component state. And now we can say that adjoint of theta is dl d theta, and this is what we want to find out. So now that we have this augmented ODE, the Jacobian of this is basically this. And we can plug this into the previous equation we used to compute it, and we can see that derivative of this augmented adjoint is equal to this. And this allows us to compute basically dl d theta. So here's a complete backprop algorithm from the paper, and let's look at the input here. The input is the parameters, the start time and the stop time. So this is at which time we get the answer, the output of our neural network. This is the actual final state, and this is the loss gradient, right? This is dl dz at t1. So what we do first is we compute the gradient with respect to t1, which is at the end of the network. And once we have that, we can define our augmented state here. An augmented state, remember, involves everything from our state to theta, to the actual augmented with the parameters theta, so we can use it to compute our theta. And our augmented dynamics is basically our adjoint including theta. So after we have that, we can use the ODE solve on this augmented dynamics, starting from S0, right? And remember, S0 starts at the z of t1. So we are starting at the end here, right? We're starting at t1 and we're going to t0. We're going backwards. And if we do that, we will find these things here. And for example, this is dl d theta. This tells us how to adjust our parameters theta to decrease the loss. Okay, so this is the end, and the paper has some interesting nice examples of the difference between how RNN fit looks versus how neural ODE fit looks. It's actually something called latent neural ODE, but regardless, it seems to model the dynamics better here. So the references here are neural ordinary differential equations. This is a paper from 2018 NIPS. This is the differential equation flux library, which is a Julia library that I use for my experiments. Neural ordinary differential equation lecture notes by Ricky T.Q. Chen, who is one of the authors of Neural ODE paper, and a link to the description of a dynamical system on the Math Insight website. Thank you. I hope it was useful, and let me know if you have any questions.